guys. Sorry for taking so long. As I promised, this is going to be the exercises that I solved today, so it's going to be available for all of you for whenever you want. Okay, I'm going to take myself off the screen because it's not following any purpose, yes, for you to know it's me. And so this is, sorry, this is where it is. Okay, I'm going to try to be. Quick about it. I know the first exercise is not so difficult. You just have to operate a little bit with matrices. And what it's just to see if you can actually operate with them or not. And this first matrix, matrix A, you see this is 3 by 3 because it has three rows. And well, it has also three columns. So you can say 3 by 3, like three rows and three columns. But matrix B has just two rows and three columns, and so it is 2 by 3. And so to see if you can actually multiply them, it's always the same. You can actually try to perform this multiplication in the order a times b or b times a, but when you do, these dimensions in the middle have to actually be the same, and so you cannot do perform a times b, but you can perform b times a. In this case, as you see, this is actually not possible, as this is not possible as well because b and a has different sizes, and so they can operate the sum operator cannot be applied here. B cannot be done like that. B squared doesn't work because the square matrices only works for square matrices, and B isn't square matrix because it has a different number of columns and rows. So, well, the other three things we can do, okay, I have here the results. I got them with Microsoft Excel, but it's just easy. I'm not gonna do every number, okay, I'm just gonna show how to get one of them, for example. And so in this case, I'm gonna get the minus 27 here, okay? And so what I do, I'm looking for the element in the first row and second column. And so what I take is the second column of the second matrix and the first row, the first one. And so this is just 1 times 1 plus minus 2 times 11 plus 3 times minus 2. So 11, this actually is minus 22 minus 6, which is minus 28, plus 1, so minus 27. Okay, so that's pretty much it. For this element, for example, the number 8, as it is the element number 2, 1, you take the second row and the first column. So that's actually how you do the trick, okay? And so this is 1 times 6 plus 0 plus, times 2 plus 1 times 2. And so this is actually 1 times 6, which is 6, plus 2, which is 8. That's pretty much it, okay? For the square, the a square, it's actually the same, but well, let's see how to get, for example, the minus 2 here and also the minus 21 here, for example. And so the minus 2, this is actually second row, third column, and the 21 is third row, second column. So what I'm gonna do first the minus 2, okay? This is actually second row here and third column here. And so you just do 2 times minus 1 plus 11 times 0 plus 0 times 0. So that's minus 2. That's pretty easy actually. And second case is third row here and second column here, which is 1 times 1 plus minus 2 times 11 plus 0 times minus 2. So that's minus 22 plus 1, which is minus 20. Okay, so that's pretty much it. You just do that for every case and you get every number. That's pretty much what it is. What about a minus 1? Well, the inverse of the matrix A is actually performed. There is a method called the Gaussian method that I think it's sometimes counterproductive to actually get there, and this is actually much easier, getting the adjunct matrix and then doing a transposition and then dividing it by the determinant of A, okay? The determinant of a is actually mm, what I'm gonna do first, okay? It is 15. We'll see, okay? This is actually, you see, if we start getting that, the determinant of a is 6 times 11 times 0, nothing. 1 times 0 times 1, nothing. 2 times minus 2 times minus 1 is actually 2 positive. Minus, and then minus 1, 11, 1. That's actually minus 11. And here is 0 minus 2, 6, and 1, uh, yeah, sorry, yeah, 1 minus 1, yeah, that is true. And so, yeah, sorry, this is minus 4, right? This is 2 minus 2, 1, this is actually 4. Yeah, I was like, what? And then minus 11, which is actually 15, okay? This is pretty much it. I was just thinking that it didn't make sense what I had done before, and so this is 4 instead of 2, okay? Yeah. I this is usually what is most important, which is realizing that you made a mistake somehow, you know? So if something doesn't make any sense, it's like, what did I do wrong, right? And so in this case, with the adjunct, what you have to do actually is for every element here, any element, for example, first element, this 0 here, okay, is actually, well, remember this is actually transposed, but for the first element, it doesn't matter, okay? What you have to do is actually perform um, two things, okay? This is called, um, first, you actually use what is called a map of signs, okay? And this map of signs actually looks like this for three or for size 3 matrices. This means that when you actually do the adjunct, whatever you get as a result, you keep the sign in those places where the sign is positive, and you change the sign in those places where the sign is negative. And to see which number actually to write somewhere, you just have to see or to actually compute the determinant of the matrix if that row and um, that row and that um, column weren't there. Okay, and so think this is the place I want to see. Okay, this is the place I want to win. This 0 here, and so I go to the original matrix. I take this place here, and I imagine the matrix doesn't have a this column and this row, okay, it's column and row, and so I perform the determinant of whatever is left. I mean, in this case, that is 0, so I keep the 0 like it is, okay, and I don't change the sign because what there's no sign to change, but also because I have the map of signs here, okay. This is usually shown like this, okay, like d y j times minus 1 to the power of I plus j. This is the minor, right? Like the minor you have left when you take out these two, the column j and the row I, and then you multiply it by minus 1 to the power of I plus j. So in those places where that addition here is positive, you keep the sign, and when that addition is negative, you actually change the sign. Okay. Of course, if we do that, for example, for this number here, I have to later do the transposition. So when I think of this position and this position, the one that I'm going to do when thinking about this one here is this 11 because I'm going to do later a transposition. So when I want to write here this 11, what I do actually is imagine that this doesn't exist and this doesn't exist. And so the determinant is up to these four numbers. So this is 1 times 0 minus 11, which is actually 11. And in this case, I again keep a sign. And you just have to do that for every uh, of the places, and that's it. Okay, that's you. Usually, you actually get every adjunct position here, and then you actually write the numbers after with the signs, and then transposition and then divided by the determinant. And so the final result is pretty much what is written here. Usually it's better to leave the whatever is in the determinant as a fraction, as a quotient, because if not, you will have here very not round numbers, and that's okay. This is just operating with matrices, okay? And well, let's go to the place you wanted to go, because this is the one that actually um, gave you some headaches, okay? This is a problem that is telling you to actually solve a system of linear equations, determining the character. I'm sorry because of this word translated is just automatically. Okay, and so it wrote it in Spanish instead of in English, but I think I did write it in English. I don't know. Anyhow, it is telling you to get this character to know if it is inconsistent or if it is consistent, depending on the value of k. And so I wrote here a couple of things. Okay, first I wrote this a augmented a or a amplified, which is a and b, and I wrote here also how to actually determine if it is consistent or not or whatever. Okay, and so what we need actually is the rank of A, because we know that if the rank of A is actually the maximum it can be, if the rank of A was to be 3, if the rank of A was 3, I know we would be in this second case, which is actually the typical case. Okay, I just have one solution, but it's actually asking me to solve the system only in the case that I have consistent but dependent. So it's asking me to get a solution only in the case that I am in the third case. Okay, what I have to do actually is to get the determinant of A and get when it would imply that the rank of A would not be 3. The only cases for that is when the determinant of A is actually 0. So I have to actually solve an equation of this determinant of A being equal to 0. What I have to do is actually get the solution to this, and the solution will be a k value, because the k is our only incognita, our only unknown, okay? So in our case, I'm gonna actually take this here, and I'm gonna actually do it, okay? What we have here is this, so I have here 1 plus k square, this is all like this, plus 1 plus k times 1 times 2, so this is 2, so 1 plus k, and this is 2, and 1 times minus 1 times 1, this is minus 1. This is the first factor, first of our determinant, and the second is 1 times 1 plus k times 2, so this is 2, 1 plus k, and here is 1 times minus 1 times 1 plus k, so this is minus 1 plus k, and last one is actually 1 plus k, 1 and 1, which is plus 1 plus k. And so you can see actually that this goes with this one and this goes with this one. And so we actually have, this is equals to 0, of course, and what we have is actually this. We have 1 plus k square minus 1 equals 0. And so we have to solve that. We use the expression of these notable products. So we can, this is a binomial or something, and so we can solve it just by applying the multiplication, or just knowing that this is just the square of the first one plus 2 times of the product of both numbers. So this is 2 times 1 times k, which is actually 2 times k, yeah, and plus k squared minus 1. And so that's equal to 0. And when we open the parentheses, we see that these two numbers also go. So we have 2k plus k squared equal 0. And so we take common factor, and so we have k times 2 plus k equals 0. And so we have actually two solutions to the system, or to this equation, sorry. We have that k can either be 0 or k can actually be minus 2. The reason is that for a product to be 0, one of these two has to be 0. So k can be 0, just like this, or 2 plus k can be 0, so k equals minus 2, and that is pretty much what it is. In these both cases, we find that the determinant of a equals 0 in both cases, okay? So we know that for every other number, the determinant of a is not 0. So for every other case, the rank of a equals the rank of a plus equals n. And so for every value that is not k equals 0 and k equals minus 2, so for every value where k is different from 0 and k is different from minus 2, for every other value, our system is consistent and independent. Independent. So we know something, okay? And so it means one solution, just one solution for the system in any case where k is different from 0 and different also from minus 2. Okay, that's what it is. And so we have to now see if for any of those values, k equals 0 and k equals minus 2, if for any of those values the system is either inconsistent or consistent but dependent. If we find that for any of those values the system is consistent and dependent, we have to solve it. If not, just say that for those both values the system is inconsistent. So what happens here? Well, what happens is that we know that the rank of A of this first part here is 0. I mean, it's 2 because the determinant is 0. So we have to actually change one of these columns and introduce B and see if actually the determinant is different from 0. And in both cases, the determinant is different. We can find a determinant that is different from 0, and so we actually have that in both cases, we are in front of a system that has no solutions. Both lead to inconsistent system, systems, inconsistent. You'll see. I'm gonna show you, okay? No problem. See here. I think I have the system over here. Yes, for minus 2, the system stays like for 0 better and for minus 2. So for 0 and for minus 2. First, for 0, okay? For 0, the system stays like this. Minus 1, 1, 2, minus 1, minus 1, minus 1, 1, 1, 1, and then 2, 3, minus 1. 2, 3, minus 1. This is A amplified in the case, or augmented A, in the case that A equals 0, okay? Sorry, in the case A equals minus 2. I'm so sorry. Yeah, I'm gonna, this is in the case that K equals minus 2, and in the case K equals 0, it is, let's see, in that case, augmented A equals 1, 1, 2, 1, 1, minus 1, 1, 1, 1, and 2, 3, 1. Okay, that's the other case. And so in both cases, we can see why the determinant was 0. In this case, because these two columns are the same, and in this case, because these two rows are the same. Okay? And we can see how in both cases, if we put this, we don't have that problem anymore. And in this other case, if we actually change and put this column here, we actually don't have that problem anymore. And so the determinants are not 0 anymore. They are not 0 anymore. And so in both cases, the rank of A amplified, because the determinant of A amplified or augmented A was different from 0, the rank of A amplified was 3. And so we are in the case of no solutions in both cases, okay? In both cases. And so we're in the case that we have actually no solutions to the system. We are in front of an inconsistent system in both cases, and so we don't have to solve it, okay? It was a tricky question, so you didn't have to actually do it. It doesn't matter. It's gonna be easier in the exam, but I just wanted to actually see if you could think about it, okay? Anyhow, the quadratic forms, even easier, okay? I wrote here also how to classify them, thinking about their um, principal minors, right? And remember, this is just to go through the classification. It will be indefinite, it doesn't fall under any other category. It will be negative definite if you have negative and positive um, um, values for the principal minors. These I and J represent the sizes of those principal minors. The same for semi-definite or negative semi-definite, but with zeros in there. Positive definite when you have every principal minor positive, and positive semi-definite when you have every principal minor being positive or zero. Remember that when you have negative semi-definite and positive semi-definite, you have to check it out for every row column transformation. Okay. In this case, you see two of them look um, actually maybe difficult at first. These A and C were really, they had a small trick, okay? Because there's a thing I told you in class that when you found that these main um, numbers, okay, that were gonna be in the main diagonal, if those numbers had opposing signs, this is negative and these two are positive, right? When that happened, immediately you could know that this matrix was associated to a quadratic form that was indefinite. The same happens here because this is actually negative again. And so you actually don't have to do this. No, no, no. This is just indefinite, just like that. So you have uh, to solve just like that, okay? In the case of AB, or the matrix A for case B, what you have is actually this, okay? Let's use the principal minors and let's see where we can classify the results, okay? First, D1 is 1. Remember, principal minors are just minors in this direction, so D1 is actually this determinant, so D1 is 1. D2 is a determinant of these four numbers, and D3 would be the determinant of these nine numbers, okay? And so D2 is actually 0 because 1, this is 1 minus 1, this is 0, and so D3 is also 0, okay? And so we know just by looking at this that the only thing that this matrix can be is positive semi-indefinite or indefinite. For classifying it as a positive semi-indefinite, we had to see that this actually uh, behaves like this for every row column transformation. And so we have had to actually transform this matrix a couple times, okay? So AB changing rows and columns 1 and 2, AB changing columns and rows 1 and 3, and AB changing columns and rows 2 and 3. I'm going to do it in just one step. Remember, I told you it's much better to actually do it in two steps, okay? 1 and 2, it's going to be exactly the same matrix because it's actually both rows and columns are exactly the same if you look at it. So not much to do here. And so these three determinants are going to be exactly the same, right? This is going to be 1, this is going to be 0, and this is going to be as well 0. With columns and rows 3 and 1 and 3, okay? It's going to be 3, 0, 0, 0, 0, 1, 1, 1, 1. And the determinants are going to be D1 is going to be 3, D2 is going to be 3, and D3 is going to be 0. So it can still be positive semi-definite. We'll see if we don't find any contradictions here in the last case, okay? With 2, 3. 2, 3 will give us a matrix that is this. 1, 0, 3, 0, 1, 0, 1. look that all of these matrices are symmetric because the first one was also symmetric. Okay. In this case, this is D1 is 1, D2 is 3, and D3 is 0. And so, yes, this matrix and this quadratic form that it is associated to is positive semi-definite. And well, that is all, guys, and I hope this is helpful, sorry to you, and well, anyhow, I'll see you in class.